Okay. Hi, everyone. Welcome to our 7th Good Meetup, this time about Apache Arrow. And I'm your host, Stepan. And you might be wondering why we chose Arrow as our, meetup topic. And it's because it's really close to our heart. Because as you can see, all of those things, the simplicity, the flexibility, the productivity and scalability of GoodData is in huge part due to Apache Arrow. But don't take my word for it. Matt will definitely tell you more, and then Jacek will show you how it looks in practice. Just some housekeeping. There will be 2 20-minute presentations. Then we will follow up with Q&A and Slido. Here is the QR code in case you want to ask questions early, but I'll share it after each presentation. Then the networking and refreshment will be after the presentation, but between the presentations, we will actually have 15 minutes. So you can grab a beer and some stuff. And if you have any questions, just ask someone with this tag, and he'll be more than happy to answer. Okay. And now into the deep dive into Apache Arrow. Please welcome Matt Topol.
Okay, so greetings, everybody, and thanks again to GoodData for having me out. This is my first time in Prague, so I'm having a blast. Great time. And so I was asked to do kind of a deep dive and go more into the internals of Apache Arrow, and then Jacek's going to follow up with how GoodData is using Arrow directly. So it kind of complements each other there. So before we begin, in case anyone somehow came here and didn't know who I was, which is actually possible. I am a PMC member on Apache Arrow project. If you're unfamiliar with the term, that is the Project Management Committee with the Apache Software Foundation. I'm also a primary developer for Iceberg Go, the Go implementation, and contribute a lot to the Arrow Go implementation, but also work on the C++ and Python. And as part of the project management committee, I help make decisions about forward looking with the format and how we go about the project. And I also am the author of In-Memory Analytics with Apache Arrow, the book on Arrow. I literally wrote the book on it, and whoever asks the best question tonight is going to get themselves a signed copy. So don't forget that QR code for the Slido, and we'll subjectively figure out who asks the best question. Okay, so quick primer on Apache Arrow. The Arrow is a in-memory column-oriented format. It's a spec, not to be confused with the Arrow project, which is the collection of libraries and implementations of that spec. Now, it came about, Arrow started in 2016 and came about because of the noticing that as data flowed from one system to another, from machine to machine, a lot of overhead happened in the serializing and deserializing of that data every time it went from one place to another. And if you're serializing and deserializing data, that means you're doing a lot of copying. So we wanted to reduce the copies, which inherently makes everything faster, but do it with something that is also useful and performant in memory to utilize. And so there's implementations of the Arrow format in a ridiculous number of programming languages. C++, Go, Python, R, Java, Ruby, Julia, MATLAB, Go, JavaScript, you name it. Now, most things, there's probably an Arrow implementation for that language. And if you're not familiar with what I mean by column-oriented or columnar, it's a very simple concept. When you're thinking about the way data is laid out in memory, typically when you think about your rows of a table, your structs, you're going to think about them in terms where you have in the actual memory one column after another. So your first column A, row 1, column B, row 1, column C, row 2, column A, row 2, column C, row 2, column C, and so on and so forth. That's row oriented. Column oriented, invert that, transpose it. You have all of the data for a given column is in a contiguous chunk of memory. Now, the reasons for doing this is that it leads to more efficient I/O. That's where things like the Parquet file format come about. Because instead of having to, if you only need to read a subset of the columns, which happens a lot with analytical workloads, where you only need one or a few columns instead of all the columns, then with a column-oriented format, you can read only the columns you need. In a row-oriented format, you'd have to read the entire row every time. You can't just find the value for a given column easily in a row-oriented format. And so by having a column-oriented format, like say Parquet on disk, you can reduce your I/O costs. And then once you bring it into memory, you need to represent it somehow in memory. Now, if you then copy it into structs, you've lost all that benefit of having it all contiguously. And then it leads to the benefits of vectorization and SIMD. At the process level, being able to do single instruction, multiple data. To do a vectorized computation requires all of the values in data to be contiguous in memory because you got to shove it into a register. If the data is not already contiguous in memory, that means you have to do a copy if you want to use vectorization. If the data is column-oriented in memory, it's already contiguous. You don't have to do a copy to benefit from the vectorization. It's already extremely friendly towards that. And so you can then utilize this by it also improves the cache locality at the processor level. If you're familiar with how processors work, you got to pull in chunks of memory at a time. And the processor is going to try to guess what your next chunk of memory is going to be. Now, the more you can pull in at one time, the fewer times that it has to go back out to memory, the faster your processing of its system goes. So by having the data column-oriented for analytical systems, ends up significantly benefiting from this. And so, as I mentioned, there's Arrow the spec, the format, and then there's the project. The Arrow project includes things like, the libraries surrounding it that implement useful protocols for interconnectedness, like Arrow Flight and Flight SQL. It includes a C data interface for passing Arrow data zero copy across a C boundary so that you can avoid copying and just pass some pointers. It also includes Nano Arrow, which is a kind of minimal vendorable C library for interacting with the Arrow format. And then you have the entire ecosystem around it. Apache Data Fusion Query Engine is all based on Arrow. Most Parquet libraries, once it decodes the data from the Parquet file, will use Arrow to represent it in memory. Then you have the big ones, BigQuery, Snowflake, all those engines. They can output data in Arrow and save you time and effort in the conversions and transpositions. Then you have all the various libraries I mentioned, and since Arrow has a spec, it means that the libraries just need to conform to the spec, and then everything plays together, creating this very large toolbox of utilities that you can benefit from. So a quick little incomplete history. Arrow started in 2016, co-created by Wes McKinney of Pandas fame and Jacques Nadeau, who was co-founder of Dremio. A couple years later, NVIDIA announces NVIDIA Rapids, their toolbox for building analytical GPU computes, which is built on Arrow. NVIDIA Rapids, the whole ecosystem of cuDF, cuML, all those things are all the Arrow format, but on the GPU. Then Arrow stabilizes with a 1.0 release. And then a couple of years later, we adopted ADBC, Arrow Database Connectivity. I'll talk a little bit more about that later. Apache Data Fusion started as a sub-project of the Arrow project, and then eventually last year graduated to become its own top-level Apache software project. So you have these libraries that are built out. The Python Arrow library, PyArrow, is downloaded hundreds of millions of times per month. It is ridiculous. And you have this series of libraries that have been created by thousands of developers over a decade. And because it's owned by the Apache Software Foundation as an open source and released as the Apache License 2.0, no single vendor controls the project or the format. It is managed by the volunteers and the PMC, who are representative of multiple companies. And so this goes even further when you start talking about things like DuckDB, who explicitly implemented a query engine, and DuckDB's internal memory representation is nearly identical to the Arrow format, which means they have very good zero-copy output and input with Arrow. And then you have Meta's Velox engine, Snowflake, BigQuery I mentioned. Pandas has great interoperability with Arrow. If you're familiar with the Python, with the Polars data frame library, it's entirely built on Arrow, specifically the Arrow Rust implementation. And then finally, there's extensions and extension types that are canonical around the community for dealing with geospatial data, GeoArrow, GeoParquet. And it's just continuously growing and getting further along. So now that I've kind of established what Arrow is, so we have a good starting point and what this does, let's take a look at how it works, why it is so useful, what's so beneficial. And so the core of Arrow is we're talking about arrays. We're talking about simple arrays of data. And so if you look at the basic primitive types, you're fixed with integers, floats, the usual things. You see a few things here. Now, one of the things that are common to all the Arrow types is this validity bitmap. It allows you to represent nulls and represent null data in a compact way and includes a little bit of metadata. You have the total length of the array, the count, the number of nulls in the array, and of course the data type itself. And then you have some number of buffers. In the case of your fixed size primitives like integers and so on, you have the validity bitmap, which if there are no nulls, you can omit that entirely. And then you have one buffer, which is just the values that you expect for the array. In this case, for an int32, you have everything is a 4-byte integer from one end to the other, length times 4 size buffer. And the reason for this is because you get constant time random access into it, and all of your data is contiguous in memory, which means it works fantastically with vectorized data. It also means it's consistent and compatible with pretty much every other library column-oriented way of representing a column of data for these types, which is why it enables it to work so well with pandas and polars and so on. And so we have the types you'd expect, and so we can move on. How about strings and other variable length binary data? So typically, when you think about like a traditional vector of strings, you're going to have a vector of these structs, which contain a length and a pointer to the data, right? That's your typical way of representing a string. So Arrow strings, instead, you have 2 buffers. Well, 3 buffers. You have the validity bitmap, which again is optional, and if there's no nulls, you can omit the validity bitmap entirely. And then you have an offsets buffer, which basically for a given index into your array tells you where the values, where the data for that value starts, which is an index into the value buffer, which is just all of the string data end to end in one single contiguous buffer. Now you can grab a slice of that and hand it off to something, and it can see the string. Again, constant time random access. Lists work the same way. You have your validity bitmap, you have a buffer of offsets, and then you have a child array. Now, the reason for the child array is because there's two levels where something could be null. You can have a null list, in which point it would be in the top level, or you can have a null element in a list. It also means that you can represent zero size lists without any overhead. Because as you can see in the value here, when you go from 0 to 3, 3 elements in the first list, next element is a 3, which means there's no elements in that next list. And you can see that doesn't even show up any undefined or any open spots in the child. The child is just all the elements of all the lists end to end. And then again, gives you this way of handling random access of constant time. And the child, because it's not integrated as part of the list, it can be of any type, complex hierarchies. You can do nested lists, structs, and so on. Fixed size lists are nice and easy. No offsets buffer because it's a fixed size. You have a validity bitmap and a child. That's it. Because you know the type, being a fixed size list of say 2, then given an index, you can immediately calculate where the values are for that index, for that list. Structs, again, very simple. You have a validity bitmap at the top level, and then you have one child for every field of the struct. That type could be any type, could be a list, it could have its own children because it's a hierarchical list. It's just straight 0. But it also means that a table can be represented as a struct without any copy cost. You just reference the arrays as they exist. You can also split your array into series of columns, again, with no copying. Just reference the existing array columns. You can add a column or remove a column because a struct is just a collection of these arrays. And so adding a new column or deleting a column doesn't require copying the entire array or any other columns. It just is adjusting a pointer to an array. And then Arrow defines other types. You have run-end encoded types. You have sparse and dense unions. You have dictionary types where you want to do dictionary encoding to save space, where you have a dictionary of some value, and then just a list of indexes into that dictionary. There's also some more higher level performance benefits from using these recently added view types for a string view or a list view, which are much more efficient if you're constructing them out of order. And I invite you guys to look at the documentation and look more into how those things are structured internally, either in the documentation or in my book, either way. But then on top of all those physical representations that we just went through, Arrow also has a bunch of logical definitions, logical types. Arrow represents Booleans using a bitmap. Very compact, very quick, very easy. And again, constant time random access. It has decimal types for enlarged precision. You have a decimal 32, 64-bit, 128, 256, etc. And then you just define a precision and a scale. And then you define the bit width. And that's how big each value is. Nice, simple, straightforward, but it's a spec that's consistent no matter what language implementation you're using. So they can all interoperate. It defines temporal types, dates, times, timestamps, using integers and the semantics that are assigned there, which makes it really, really easy to take data from one system to another, from one language to another in a zero-copy way. And then you build on this. Arrow has a schema definition for a record batch, which contains schema level and column level metadata so that you can easily be self-describing. Arrow, when passed around, is completely self-describing. And then a series of these record batches can be all put together, again, zero copy, just shifting around pointers to create a table. And then you can independently interact with this table as if it was one contiguous giant table, except internally it's chunked. And you can build it you can build it chunked because it doesn't require all of them to have the same chunking in each column. It only becomes an issue when you start passing it around. You just grab the smallest chunk and use that. And you can slice. You can do zero-copy slicing of your records. And so everything's all built around this idea of reducing and limiting the amount of times you have to perform a copy. Okay, but it also speeds up computation because of that idea of having that validity, bitmap, and the data buffers. Think about this. You have an array of integers, and you want to add a scalar value to every element of the array. But some of those values might be null, right? But you want to use vectorization. Well, typically, what you do is you loop over the values. You check whether a value is null. And if it's not null, you add 2. If it is null, you leave it null and you move on, right? With Arrow, you can split it up and parallelize. You take the validity bitmap and just boom, the same validity. You're just adding a scalar value, which means the validity is not going to change. If it's null, it stays null, right? So you can just reuse the validity bitmap. No changes there. And then you can vectorize, just add 2 to every element. The end result is exactly the same, but now you've benefited from vectorization, single instruction, multiple data, and your computation is going to be significantly faster. If you're doing a computation with 2 columns, as long as you define the semantics of if one or the other is null, what happens to the result, you can do a bitmap and a bitwise and or however you like on the validity bitmaps of your arguments, and then vectorize the operation of the data. And you end up being able to benefit from this vectorization and increasingly perform more and more computations with less hardware and improved performance. So going a little bit further as I wrap this up, just some ideas that Jacek is going to be showing how GoodData is taking advantage of is, for example, Arrow Flight. The Arrow project, the Arrow spec specifies a standardized data transport across gRPC. And the idea here is, again, since Arrow data, you don't have that serialized and deserialized overhead, it means that you can more easily parallelize the data, the fetching. You have this very efficient query execution, retrieve data without this overhead of copies and deserialization. And the end result is you get significantly better throughput. And then there's things like ADBC, Arrow Database Connectivity. If you're familiar with ODBC or JDBC, similar concept, client API, swappable drivers that implement the API. But ODBC and JDBC are row-oriented inherently. And about 90% of all analytical data systems now are all column-oriented, which means the modern data stack is currently compute everything in a column-oriented way for vectorization, transpose it all back into rows to pass it across ODBC and JDBC that were developed in the early 90s, and then half the time transpose it back into columns for your visualization, other applications, your data frames, and so on. There's a lot of time lost in those transposes. But also you have this standard. Adopting a standard means that you get the benefits of interoperability across all these tools, across the entire landscape and ecosystem. You get to pick whatever's best for your use case. And so like I mentioned, ADBC, those images looked better before. Should not be over covering that. Never mind, move on. And then some short little case studies here. Apache Data Fusion. You want your Spark to be faster, but you can't use Databricks? Well, guess what? A bunch of people got together and they built Comet, which is a Spark executor that just embeds Apache Data Fusion. They let Spark handle the compatibility, and they let Spark handle the planning and orchestration, but the speed and performance of the computation is handled by Apache Data Fusion, which is built on Arrow, which then, if you know much about Spark, the data in Spark is in your JVM, and you want to pass it across to this Rust compute engine. You don't want to pay the cost of copies and serialize. With Arrow, they just have a little bit of metadata and pass pointers across. And it works because it's the Arrow spec, the Arrow format. It's represented the same way, no matter what language you're in. I mentioned libqdf and NVIDIA Rapids. Same idea. By using Arrow on the GPU, they're doing it for all the same benefits you would get by doing it on the CPU, except benefiting even further because it's on GPUs, which are much better at the vectorization. And recently, I contributed to libqdf a bunch of changes to allow getting your Arrow data in and out of libqdf without having to do the copy from GPU to CPU. You can keep the data on the device and hand it off or get it back from libqdf without that copy. It stays on the GPU. So the whole thing to think about is that columnar, column-oriented, if you're doing analytical data computation, is just going to be faster. If your system is truly row-oriented, transactional, and in that route, which is the minority case now in modern data analysis, then yes, stick with your row-oriented stuff. But if you're doing bulk analytical data compute, you want a column-oriented system, which is why nearly all the compute engines are like that for analytics. And this becomes easily accessible via Data Fusion, DuckDB, Velox, all these systems that you can use whatever makes the most sense engine-wise for your use case. And then you have all these core libraries that just build on the stable foundation of the spec of the project, powered by all this open source collaboration and integration for all your analytics. Okay, it's an enormously diverse ecosystem with tons of contributors that hopefully some of you will become contributors too, maybe. So if you want to learn more about Arrow, if you want to get more ideas here, obviously look at the docs, get my book, lots of examples. I cover Python, C++, and Go in the book because I emphasize the interoperability, the fact that you can communicate efficiently between different programming languages. And the publisher, Pact, my publisher, set up a link, and this QR code will take you right to Pact's website for the book. And there is a 25% discount code, 25 Apache, that is currently, it's only available if you're getting it on Pact's website to use the discount code. But the book is also available on Amazon. But if you want to get the book, ebook or physical, either way, you can use this discount code and get 25% off. With that, that's what I got.
Thank you very much, Matt. All right, now is the time for questions. And before we get questions on Slido, is there actually anyone in the audience who wants to compete for the book and ask a question? Yeah, live.
I don't have a good question, but actually I missed a little in the presentation some like long-term view into the future, like what the community plans in far future. Is there any like ultimate and exciting goal you would like to achieve in upcoming, let's say 2 years?
I mean, the biggest goal we want right now is to get more adoption of ADBC, both in applications and in database systems. Like if your data system exposes an Arrow Flight SQL interface, then you get all your client connectivity for free because there's already ADBC Flight SQL driver. There is already a JDBC and ODBC driver for Arrow Flight SQL. So if your system exposes Arrow Flight SQL, you get all the client connectivity for free, and you don't even have to build it or maintain it yourself. So getting that adoption of ADBC so that more applications have connectivity and more databases have drivers is one of the bigger things we're dealing with. But also the use cases for ML and AI and non-CPU devices and those interfaces.
Is like are the leaders of the project already in touch with legacy vendors like, for instance, Oracle And are you trying to convince them to like expose Arrow?
I mean, Arrow as a project, there's contributors, committers, PMC members from a whole host of different companies. I don't offhand know anyone talking with Oracle, but I know that some of us are definitely communicating with Microsoft and Power BI. Obviously, with my work at Voltron Data, I've worked with Snowflake, and we built out the ADBC Snowflake driver. I communicated with Google about BigQuery to get them to expose Arrow stuff in the driver that they already had, so that we can build a BigQuery ADBC driver. And so it's very much, you know, a one-to-one. You know, it's reaching out and getting it, but a lot of it's also advocacy of developers like you guys who like find it interesting, play around with it, and then advocate for it in your own organizations. And, you know, a lot of this comes down to that because it's an open source project. It's Apache. You know, it thrives on the community.
All right, thank you. And the other question is whether you heard that Polars rewrote their string representation because they didn't fit the default Arrow implementation.
Well, that leads into the string view and binary view thing I talked about. There's a research group in University of Munich that built out this system UmbraDB, and they built out what was called German style strings, which then got adopted by DuckDB, Velox, and Polars, and how to represent the strings. And to maintain and create that zero copy communication, DuckDB and Velox reached out to a company I worked for, Voltron Data, and we worked and eventually added those string view types to the Arrow spec. And Polars re-implementation, it matches the string view that we were talking about here. And so now Polars handling of string views matches a defined type in the Arrow spec, because as they saw, and as DuckDB saw, and as others saw, that type is just better for a lot of join use cases and otherwise. And that kind of proves a lot of the benefit of open source and the fact that we're actively maintaining Arrow to make sure that when research moves forward and we discover new ways of doing stuff, the Arrow community is staying on top of it. When we see new ways of implementing and new ways of improving, we'll add new data types if they become necessary to help keep with the times.
Okay, thank you. And the other question is that you mentioned high precision numerical format. And what is it about float 16 that makes it not supported by e.g. Parquet?
Good question there, except float 16 is supported by Parquet. We pushed through the addition of a float 16 type to Parquet, which is represented just using a 2-byte fixed, a fixed size 2-byte physical type. And they added the logical float 16 to it. For the high precision, I mean, it's just a matter of, most of the time, it's just a matter of someone needs to propose it, champion it, and help push it through the specific committees and get the votes and actually create the implementations of it. That's what most of it is. It's all open source stuff. And so the reason why there wasn't a float 16 in Parquet is because no one had yet done it. And then they made the argument to the project management committee, create some implementations, got the votes, and then it became part of the Parquet standard now.
Okay, thank you. And last question before the break. And what are the plans to improve data file storage? And is the Parquet the best thing we could get?
I mean, Arrow is not a file format. It is an in-memory format. There are groups trying to improve upon Parquet for file storage. You've got LanceDB, who are building on a format that's sort of based on Parquet a bit, but they've kind of done certain changes and things to work amongst and make it better for ML workflows and vectorized and vector searches and vector handling. Meta started work on a Nimble file format. They call it Nimble, which same idea is they're trying to improve point lookups and other AI and ML use cases. So in the community wise, there's definitely work happening for better file formats and data storage, but that's not where Arrow lies. But Arrow does rely on the interoperability with those formats of once you get the data from the disk and read it into memory, can it easily be represented as Arrow? If it can't, why not? We should work with those groups to help make sure of that. LanceDB, for example, with their entire Lance file format, they use Arrow internally for all their in-memory handling already. And so that interoperability is very important for that handling.
All right, that wraps it up for now.
I do want to answer the last one, that is Arrow Parquet killer, because Arrow and Parquet are complementary. They serve different purposes. Parquet is your on-disk. It is encoded, compressed. It's designed to improve I/O query execution in skipping the I/O and stuff like that. Arrow is how you lay the bytes out in memory. So they aren't competing against each other. They are complementary technologies.
Okay, so just really quick.
Yeah.
What's your favorite use case?
Currently, my favorite use case for Arrow has been the interoperability on GPU devices and trying to get ML libraries to adopt and support Arrow to let you just mix and match PyTorch, TensorFlow, whatever library you want, and have it not have to copy and transform the data as you go in between library for library. That's my current favorite use case. My other favorite use case is ADBC, the database connectivity side of things.
Okay, thank you very much for answering the questions. And we will see you after the next presentation. Now it's time for 10-minute breather. All right. Now Jacek will talk about how arrows should fly in BI. He'll give you some practical insight into how we use Arrow in GoodData. Okay, so give it to Jacek.
So I will be talking, well, my presentation won't be that low level, definitely. I am not that experienced in this area. First of all, I would like to thank Matt to travel so far from his home to Prague. Hopefully he will rest well here from what is happening in his country now. So I'll be talking about business intelligence use case, obviously, because we are GoodData, business intelligence platform. And I'll be talking about how exactly we use Arrow and Arrow Flight and also other open source technologies in our platform. But before I start, let's make it more interactive. I would like to know my audience a little bit more, even though I know a lot of people here already, but there are new faces. So please raise your hand who is satisfied with how quickly your dashboards are rendered or loaded. Anyone is satisfied with that? One person. Karle, don't lie. This is internal trolling. Okay, so almost nobody is satisfied, yeah? Because the status quo, yeah? So the current status quo is that you have business intelligence platform and it's connected to data sources, yeah? You can upload just CSV file. Usually companies start with some OLTP database because that's what they first need. They first need build a business case, some application for their users, and management of the application requires OLTP database like Oracle or Postgres or Microsoft SQL Server. Yeah, and then later they realize that they want to do some analytics, but they don't have power and skill set to bring new database and build some ELT pipeline. So they directly connect business intelligence to Postgres, for example. Worst case scenario. Then they realize that it doesn't scale, it doesn't work, so they move to some data warehouse technology. Yeah, currently most popular is obviously Snowflake, and Databricks is chasing Snowflake. There is BigQuery, Redshift, and many others. And the main difference here is that they use columnar formats. Matt already talked about columnar formats a lot, so you now know why it's so beneficial in analytics use case. And some of them also provide something what is called horizontal scalability. Yeah, so you can scale the cluster horizontally, and with rising number of users and rising data volumes and the complexity of the SQL queries, you can scale up. Yeah, but there are problems in this status quo. First of all, when you start, for example, with Postgres or CSV file, it's slow. Yeah. Then you realize that you can't scale. So you use data warehouse and you scale up. And finally, you realize that you are out of your money, yeah, because it's too expensive. And why? Because traditional data warehouses are expensive because their design. Yeah, they work with columnar formats, but you need to fetch Parquet files from some remote object storage, and you have to do a lot of things in between. And also because they are clustered, it means that with rising number of users, there is a high content, there is a high concurrency on the catalog, yeah, because catalog is shared by all nodes in the cluster. So when you change the catalog, you have to apply to all nodes. You have to apply global logs, and this doesn't scale with number of users. So like you can let 500 users to run queries at the same time against Snowflake. You can scale Snowflake up. But once you have 10,000 of active users or even million of active users, it doesn't work. Or you basically have to pay a lot, like hundreds of millions of dollars to Snowflake. Yeah. The only solution we currently have in most business intelligence platforms is business intelligence platform caching. Yeah. There are various kinds of caches, like Tableau, for example. They have their own proprietary database, and you can store caches there and run everything on top of these caches. Yeah. Power BI has their data marts. Yeah. For example, Cube.js, it's our competitor. They build caching on top of Arrow and on top of Apache Data Fusion. So like there are first steps in this area, but usually these caches, the maintenance of these caches is very cumbersome. Yeah. Finally, you realize that like it's fast against these caches, but when you want to refresh these caches, you are waiting for hours. Yeah. So what's the real solution, or at least we GoodData think is that this is the real solution. We believe that the last mile should be natively built on top of Arrow and also Arrow Flight. And I will be talking about it, like why later. This is just very, very short summary of why Arrow is a good idea in this area. Everything what you can see here on this slide actually was described much better by Matt in the previous presentation. So I won't spend much time on this slide. But what I'm trying to say here in my presentation is that Arrow and Arrow Flight is actually not enough. Yeah. Because Arrow is just a format. Arrow Flight is just a specification of gRPC server. But when you want to build some robust solution for BI caching, for some like data transformation services, and there are many other use cases in the BI you want to do locally in the BI, When you want to build something like that, you have to write a lot of boilerplate code. Yeah. You have to maintain the gRPC server. It must be running in high availability setup. You have to store somewhere the metadata catalog about your arrows. Yeah. You have to have some kind of eventing so you can control various processes running on different nodes in the cluster somehow. Yeah, you need some kind of observability. You have to apply some limits so some customer won't spend all your hardware resources, and so on and so on. Yeah, and that's exactly why we built our solution. And actually, this solution is GoodData agnostic. And some people from GoodData, but unfortunately not our CEO, think that we should open source it. Yeah. This framework we have built provides everything you need for running these data services. So there is a template for gRPC server, and you have to write just the business logic in this data service, and everything around is already prepared for you. And there are even like pre-built services, data services, which are implemented by us. Specifically, they are various data source connectors. So you can, for example, connect to Postgres database or Snowflake or files in object storage. Then you can stream these data and store them in caches. There is a transparent caching layer. And for every step in this ecosystem, for every data service, you can always apply caching. You can sync to caches, and you don't need to take care of it. Yeah, the cache is somewhere stored. You have a pointer to that, and you don't know where the cache, on which node the cache is stored, if it is stored in memory or on disk or only in object storage. And promoting and demounting of these caches is managed by what we already prepared. There is also SQL service because obviously we are doing business intelligence. We need to crunch data somehow. And when we started working on this data service, we did some quick prototyping, and we decided to start with DuckDB. It was also mentioned by Matt already that DuckDB is basically Arrow native. You can do zero copy operations with DuckDB. So we decided to go with DuckDB as a SQL processing engine, but obviously DuckDB is just single node in process database engine, so it doesn't scale horizontally. So in the future, we are thinking about like alternatives. And last but not least, and that's very common use case, so we decided to implement a pre-built service for our developers. There is a data frame service. Yeah. So you can very quickly build a service which interface is data frame, and our ecosystem will prepare a data frame for you. And starting from input data frame, you can apply any transformations you want. So for example, we implemented pivoting, sorting, paging, all this stuff which is like typical in the analytics. We built into one service. Another service provides some basic machine learning use case. Yeah? So for instance, you can do time series forecasting. Yeah? Input is the data frame, and based on this data frame, you quickly apply some ARIMA model and calculate required number of future data points. Yeah? And there are other use cases, but this is not actually, it's not important how many services are there, but it's important that there is a layer, convenient layer for developers, and they don't need to take care of anything, just they get the data frame and they return a data frame. That's all. Yeah. This is architecture picture of the platform or the framework. It was created by my colleague. That's why it's so awful. So what you can see here is exactly what I just described here. So there is a data frame service, there is DuckDB service, SQL service. There are connectors, various connectors. Obviously, there is ODBC, but you can also use some custom connectors. Like, for example, we built a direct connection with Google Spreadsheets. Yeah? So you can use Google Spreadsheets as a data source. It's automatically cached in the caching service. And then any visualization, any dashboard related to this data source is calculated on top of our Arrow Flight caches and not on top of the spreadsheet, obviously. Maybe, yeah, the data frame service is quite interesting. There is something happening recently. For a very long time, we have used pandas for all data frame operations, but actually pandas is very slow, even though you use Arrow as an input format. And that's exactly why we decided to migrate to polars. So currently, there are people here from GoodData who can like explain you exactly in which stage of migration we are currently. I am not sure, but I am sure that a couple of services are already migrated to polars. Okay. Live demo. So let me show you. Just it will be very short. Yeah. So first of all, this is my Docker Compose. It actually doesn't contain GoodData. It contains just this this stack, yeah, the longbow stack. It's very modular. You can run all these services in one container. That's also possible. You can configure which modules are loaded during the startup into the server. So you can collocate all use cases into one container, but you can also run every service in separate container. And we also provide Helm chart. And in this Helm chart, you can even scale horizontally each service separately. Yeah. So some services can be quite resource demanding, like DuckDB service, for example. So you can assign like more replicas and more resources to this service in Kubernetes, and other service can run just into replicas for high availability. There is also Minayo as a simulation of AWS S3 storage. That's for purpose of this demo. It's not a part of the platform. And there is also Postgres database running in this Docker Compose to support my demo. Okay, so that's okay. Source code of the demo. This is not the source code. This is the source code. So anyone knows? Actually, I name it like this, so it's not it won't be hard for you to answer this question. But anyone knows from where this query is? This SQL query. So who knows TPCH? Not that many people. Interesting, interesting. So TPCH is a benchmark. TPC is an organization. I don't know what this acronym really mean. And they have various benchmarks for various use cases. There is TPCC for OLTP workload. There is TPCH and TPCDS for like ETL and analytical workload. And there are tens of queries usually defined, and there is underlying model, data model, physical model, and there is also a data generator. So you can generate various scales of the data. In this case, I use scale 1, so just 1 gigabyte of data. There are like millions of rows in biggest tables. So it's not that big, but you can generate much more. This query is actually configurable. As you can see, there are some placeholders, so you can dynamically change which column you use for aggregation. And also you can change the date filter from the outside. This is basically the code. This is too big. Yeah, okay. So this is how you can use the longbow. Actually, we name it internally Quiver, so don't be confused. Unfortunately, we couldn't use Quiver for the public name because our legal team rejected it because there are some like other companies using this name. So it's just an internal name. What you can see here is exactly how developer can compose various use cases from this platform together. Yeah, so you can define that you want to read from some Parquet file in some S3 storage. That's like one definition of the table. And another definition of the table is just a line item table which is taken from some database. Yeah. And then the query, the SQL statement is applied on these two virtual tables, and the result is synced into the cache. But not only the result, actually, but you can also sync each step, each sub-step into the cache. And you have like you are absolutely free in that. You can implement whatever you want. Yeah. But in my case, I decided to cache also these intermediate steps, and you will see the benefit in a while. Yeah. So you can combine like any data sources. Data source connectors are responsible for taking data from these data sources. Then you can say that even raw select from these sources is cached, and then you can run SQL query with the DuckDB data service on top of these two tables, get the result, and then I could pass it to some another call of the data service and apply some transformation, and so on and so on. Yeah. So this is like how composable the whole ecosystem is. And this will be the result. This is not it. Okay. So now it failed. Perfect. Cool. I don't need it. Connection refused. So something, okay. So you can see how nice logs we have, yeah. And it's still starting. A replication started. And now let's try it again. Aha, okay, I killed the Streamlit application. I am an idiot. So lower than expected. It never happened. I swear, it never happened. I presented this in Austin, in Data Day in Austin, and it worked even there, and the risk there was much bigger. Cool. Okay, so what you can see here, it's a simple Streamlit application. There are some like inputs you can define as an end user. You can define cache key and override the caching. You can define the source database, so you can combine data from AWS S3 with Postgres or with Snowflake. We can test both. And then you can change the aggregation column as well as the filters. Yeah. And so let me try to calculate it with Snowflake. Perfect. 7 seconds. That's what I expected. So to crawl data from Snowflake, crawl data from S3, combine them, crunch them with DuckDB, it took 7.5 seconds. Yeah. And now I will just rerun the same setup. Yeah. 30 milliseconds. So this is how much it takes to get the result from in-memory Arrow store. Yeah. And it costs like literally nothing. Yeah. So it's not only about that it's like 50 times faster, but what's also important that you are serving end users, and imagine that there are like hundreds of thousands end users, and you let them to execute queries in Snowflake. So how much it will cost versus you let them to just pick these arrows from memory in 30 milliseconds and with almost zero resource consumption. So you can, like with just few nodes in AWS, you can serve million users and you are still okay and it's quite cheap. Okay, but it's just a cache hit. That's well, no big deal. So let's change the aggregation column. So what happened now? So the same query was executed, a different query was executed, but it was executed against the same tables which were already synced in a substeps, as I described like a minute ago. Yeah. So now what had to happen, these gigabytes had to be joined in DuckDB, and then the result had to be served to the client. And it took 800 milliseconds. So it's 10 times faster to crunch arrows with DuckDB than to crunch the data in Snowflake. And way cheaper. Yeah. We can also like change the filter. So let's move it to, I don't know, 1995. Anyone is experienced with Streamlit? Okay, so again, 900 milliseconds when I change the filter. And now I can also show you a line chart. I did it today, yeah. I'm so proud of it. Okay, okay, so let's go back to the presentation. But we want more every time, right? We want more. So what I have just presented, I have just presented a stack where you can crunch quite large data. You can build new data services easily as a developer. Everything this is great, but this is actually not enough, right? Because business end users will not write SQL queries, right? So you need some kind of self-service experience, drag and drop experience in dashboard builder or visualization builder. Currently, obviously, you need an AI chatbot as well. So natural language interface for business end users. So for everything this, you can't have just this basic layer, but you have to have something more on top of it. And what we do here in GoodData is that we combine it with the semantic layer. So everything what is stored in these data sources can be logically described in logical data model. You can build some higher level metrics on top of that. And then you can provide these entities to business end users so they can drag and drop them. And now even they can like ask for them in the AI chatbot. So for everything this, what is like pink on this picture is exactly what I presented today. And everything around is like the added value of business intelligence platform, in this case, GoodData. And so now next later, so what we plan, yeah, so currently we recently released something what we call Flex Connect. And Flex Connect is basically a supplement to this what I have just presented. You can build an external service, and it can be running in your premise. This external service again is Arrow Flight gRPC server. You can connect it to, for example, to your APIs or to any inference of machine learning model. And the contract is Arrow table. And then you can connect this server to GoodData, to the semantic layer. So you will see a virtual table in GoodData, and it will represent this external server. Yeah. So for example, you can do prediction in Databricks with machine learning. From Databricks, you can expose it as an API. On top of that, you can build this server. And again, the boilerplate code is available for you on GitHub. It's open source. And once you build this simple server, you expose it as a logical table into GoodData. And you can combine it with any other data set as long as there is a logical connection. So if there is a shared attribute, for example, shared dimension between this external logical data set and some, let's say, Snowflake data set, you can combine them together in a single visualization. And that's called data blending. In a far future or midterm future, we plan to build data marts. They already were in our old platform. Someone maybe remember, but they are not in the new GoodData platform, but we would like to build them with this Arrow and Arrow Flight stack. Yeah, so we allow users to crawl much more data from their data sources and keep them in GoodData in these data marts. But it basically will look like similarly like what I presented with the demo. Yeah, so you crawl these sources, we store them as arrows, and we transparently expose them to the platform. Yeah. And even like in far future, we would like, that's my dream, personal dream. I would like to implement something what we call smart caching. Yeah. So we have metadata about these data sources, but we also have metadata about the usage, how much each data set is used, each metric, each visualization, how often they are used, and in which way they are used, how they are filtered, yeah, how they are like sliced, and so on. So we have everything we need to be able to decide like what caches, what shared caches it would make sense to build and maintain in long term in the platform. And that's all. Funny picture in the end. And that's all from me. Thank you.
Thank you. And oh shit. And now on to the Q&A. 1 second, I'll just share my screen. Okay, and now on to the during data day, you mentioned DuckDB in the context of AI. Is there any synergy between LLM, Apache Arrow, and DuckDB?
Who is responsible for this question? Raise your hand. You will be punished. Okay, so in reality, we actually use DuckDB as a vector database, but very soon we plan to replace it with something, let's say, useful. DuckDB tried to ride the hype of AI, so they built a first-class support for vectorization, for like creation of the embeddings and calling functions like cosine distance or in a product. But like the feature set and the stability of the solution is not great. And after the hype, like they stopped any development in this area. So, but like the connection between DuckDB and AI, I can see only this connection. I can't see any other connection.
All right, thank you. And let me follow up with another question.
Maybe like there is also like the question was also related to Arrow, and this is maybe more for Matt. Do you have any comment on how Arrow can like help with AI?
I mean, there's everything I said earlier about how the connection of Arrow uses kind of a unifier of AI and ML libraries, where right now you can use it with already because Arrow communicates with DLPack and NumPy and other things which are accessible with TensorFlow and PyTorch and your usual the usual suspects there. But then you can go further with like libcuDF, and if these tools and libraries are only going to add support to consume and produce Arrow, if the users of those tools and libraries bug them to do so. And you know, the advantage you get there is that interoperability, the fact that you can mix and match and compose the libraries that you want with little to no overhead. And so that I was at FOSDEM last weekend in Brussels, and I gave a talk on this topic of there's some of that already with libcuDF and some of those, and you can convert to NumPy ND arrays, but it would be even better if those libraries, PyTorch, TensorFlow, XGBoost, and all those, if they directly supported Arrow, which would then increase the possible AI and ML opportunities. But then there's also other companies that are consolidating around Arrow, LanceDB, Baoplan, and a few other companies that are building AI and ML tools like Spice AI also that are utilizing Arrow as their primary data transport mechanism and they're trying their data format while leveraging all these tools and caching and stuff like you guys are with AI. So
okay.
It's a lot of consolidation going on that where everything is still coming down to Arrow is the format to use to communicate and get more and more of these tools to support it.
Okay. It's not so sexy like to add more hardware like what OpenAI does, but it makes sense. Okay.
All right. Are you using etcd for meta catalog?
Yeah,
Why?
that was mentioned on the picture. Yes, we decided to use etcd. There are some like flame wars about it in our company. Well, we decided to use etcd especially because it's native in Kubernetes. Even Kubernetes itself uses etcd, right? And you can run it in a cluster in highly available mode, which is great. And it performs quite well. But like later, we realized that it has its limits. Like when we put hundreds of thousands or even millions of records into etcd, it doesn't work that well. So like temporarily, we have etcd. We are thinking about an alternative. And we utilize basically all the feature set from etcd. It's not only about that it serves as a catalog, but it's also about eventing, for example. Yeah, so like nodes in the cluster can be controlled through this eventing. You can like control which process can be started, and so on. Yeah. Okay.
All right, thank you. Okay, and Arrow is in memory format. When you cache the full raw data, how do you go between memory and disk?
Yeah, this is a great question for someone else. Okay, but I can answer it high level. Yeah, so what we implemented is some system for automatic and also configurable promotion and demotion between memory, disk, and object storage. But for now, everywhere we store arrows, even on disk and in object storage, because it's possible to serialize arrow into file. Yeah, that's possible. But in the future, we are thinking about to store like in the persistent layer in object storage, we plan to store iceberg tables.
One thing I can point out is that with Arrow's IPC format is essentially a small flat buffer header with the raw data buffer bytes, which means that for large amounts of data, for large scale data, it's actually extremely useful to write it to disk and then memory map it. If anyone's familiar with Hugging Face, the way that their datasets library works is that you're downloading Parquet files, and their entire local cache is just Arrow files, because it enables you to memory map the file, and then you can process a larger than memory data set without blowing out your RAM. You can process 5 columns of a 100 gigabyte data set and only use a couple hundred megabytes of actual memory, because of the fact that the Arrow data is, there's no serialized, deserialized. The raw bytes are what's on disk. So you can memory map it and then only have to actually allocate the memory you need for what you read at the moment you read it. For smaller amounts of data, it may not be as economical, but for large data, it works perfectly.
Okay, and about your dream of smart caching, is it really, has any competitor already made it true?
No. There are, as far as I know, there are some projects on universities in Germany, but no one succeeded yet. And to be honest, I don't know what is the reason. Like in GoodData, the reason is the prioritization and the reality of the business. Yeah, but in other companies and universities, I don't know like why nobody succeeded yet.
Let me follow it up with the next question. Is it needed?
I think so. Like, okay, so there is one example, and that's a Cube.js company. They also provide some business intelligence. It's like more low level than GoodData, but quite, and they used, by the way, Apache Data Fusion for the caching layer. And what they do, they allow developers to define these caches manually. So you can like think about the workload, what users typically do, and then manually in the YAML file, you can define like how the cube should look like. And then Cube.js automatically pulls this data into this caching layer, into the data fusion. And it's quite good, but imagine that you have like hundreds of tables, and that's actually quite typical in larger companies. And you would need to define like thousands of these caches. And it's not only about to bootstrap, but it's also about long-term maintenance. Yeah? You would have to maintain somehow this bunch of caches. Yeah? And then imagine that you would remove column, and then you would like invalidate hundreds of caches, and then you would have to manually fix it. Yeah? So automatically design these caches. Maybe there can be human in the loop. Like you can get alerts and then like validate, yes, it makes sense. But have some tool to automatically design these caches would be extremely valuable.
I mean, I can imagine a AI smart caching type thing that could essentially do preemptive caching. You know, if you have a good enough model, you could potentially, you know, if you know what's the average for the users, you know what's average use cases, if you have the right models, you could essentially preemptively cache data with a smart enough system.
Yeah.
And then that, you know, that means you can essentially prevent that first call.
That's the idea. I like typically there is an ETL process and it updates the raw data once per day. That's quite typical. Yeah. And it's happening outside the business peak hours. Yeah. And once this happens, you could preemptively fill these caches before starting business hours. And then first users would come and everything would be fast from very beginning. On the other hand, there are use cases like you want to analyze what's happening in some Kafka queue with granularity of 10 seconds and predict something. So in this case, obviously, this kind of cache would be useless. Yeah, but for standard use cases, for quite typical use cases, this would help a lot.
All right. And have you researched the relationship between the speed and the data size?
Between degradation speed and increased data. I'm not sure I understand the question. Sorry. Maybe it's too late for me.
Does the anonymous person wish to stand up to clarify?
Carla,
Karel?
I guess not.
sorry.
All right, let's skip it. Has there been demand for computing derived data through control pipelines versus the on-demand via caching?
Computing derived data through controlled pipelines.
Does that fit more into the smart caching type thing essentially? Like you leveraging existing caches to derive versus just on-demand caching the new results? Maybe. Not sure what this is asking either.
Through control pipelines. So I'm not sure what exactly control pipelines in this case means. Does it mean like some kind of ETL pipelines or?
Does Mikhail or Michael want to clarify?
So the question is like, is there a demand like from customers to build ETL pipelines and have everything controlled and not do any kind of on-demand caching? Do I understand it well? Yes.
Yeah, thumbs up.
Well, that's a good question. Like pipelines is the most painful thing in the data stacks. I think everyone knows it. It's a nightmare, yeah? And you can also see how many tools there are in this part of the data stack and how fragile it is. Okay, there is DBT. It became quite a standard, but still building the data pipelines and maintain it is very painful. So what we can see much more often is actually that our customers would like to use our Flex Connect feature, which I mentioned in my presentation. So instead of building ETL pipelines, they would like to connect directly API and Kafka topic and Snowflake tables and Google spreadsheets. And they don't want to build a robust data pipeline for this because they know that in their organization, it would take like 5 years. Yeah? But adding one source by another with this Flex Connect function and have everything under control because function is implemented by their developers, not by us, sometimes by our professional services, okay, but yes, they can have it under control. It's preferred, but sooner or later, when you like connect these isolated data sources, you realize that there is data inconsistency. Yeah? Some data cleansing is required and you need to join these data sources. And then there is no other way than to bring some Snowflake into the picture and consolidate the data and cleanse them on one place. But like for ad hoc connection of some very simple data source, actually controlled pipelines, it's not a preferred solution.
And if the same data requests are fired off at the same time, does the cache handle it? Is it essentially race-free?
Yes. The short answer is yes. And long answer, unfortunately, I am not the right person to answer it because I don't know how does it work under the hood. But yes, it's race-free. And I think like it's especially important component in this story is the etcd.
All right. I think that wraps it up for tonight. And don't forget to ask more questions in person. You can win this awesome book. And
who do people think asked the best question so far? Does anyone have any input? Stefan?
you're the one giving it away.
Yeah, but I don't want to be lateral. Don't give me that much power. Come on. Give input. What do you think? Who asked the best question so far?
Well, there was only one who was brave enough to
put their name
tell
on
their
it.
name.
Yeah, but maybe someone else. I don't know. Which question was the best question so far, everybody? You know what? I'm just gonna give it to the one person who's brave enough to put their name on there. Michael, whatever I'm butchering. I don't want to hurt you.
Yeah.
Yeah, there you go. There you go. The only person brave enough to put their name on the question.
Finally.
There you go.
But to be fair, I really like the question about MacBook, but Okay. Thank you very much all for coming, and stick with us. Have a conversation. Ask them in person.
We're going to be around and ask questions. Come chat. It'd be great.
Okay, and there's pizza in back, so be sure to enjoy. Thank you.